The human ear can hear frequencies from around 20 hertz to about, that would be 20 hertz is a very low base, to up to around 20,000 hertz. This is way up there. And if it's a frequency above this is the range we can hear. If the frequency lies above this range, we give it a special name. We call it ultrasound or ultrasonic. And this does more than just annoy animals. This has a practical purpose. If you wanted to do some medical imaging or figure out what's going on in the human body. So say here's a portion of the human body and there's maybe a vital organ or some tissue here or some tissue over here. You're worried something's going wrong. You got to figure out what's going on inside. You can operate, but that obviously sucks. You want to try to avoid an operation if possible. You can do x-ray, but too much exposure to radiation is bad too. So a very good option is usually ultrasound. So we can take what's called a transducer. You put that transducer up to the skin. This transducer takes electrical energy, you plug it into the wall, turns it into sound energy. You send out sound waves, you send out a pulse. So this transducer sends out a pulse. This pulse travels toward anything in here, and it turns out it'll reflect. It'll reflect anytime there's a difference in the medium. So anytime there's an interface between the two media, which in this case we'll make it simple. Let's just say there's tissue from blood or other things, tissue from organs, and then the red will represent the blood. So this is going to keep traveling here. It keeps traveling. Once there's an interface here between blood and tissue, it'll reflect, comes back. And this transducer is always timing. It knows when it sent out the pulse, and it knows when that pulse got reflected back. It also knows the speed of sound, so it can calculate, all right, if it took that long to get back, it must have reflected this far away, something's at this point. And that's not done yet, though. Some of this wave is going to travel on. In fact, most of this wave travels through, keeps going. Here's another interface between tissue and blood, so it's going to reflect again. This reflects back. We'll get another pulse. This is at some later time, and the transducer knows, all right, took that long, now there must have been something else there. My one pulse got reflected 2 times. So there's something here, and here's the end of it. But that's not done either. This keeps on going. It'll reflect against this interface between blood and tissue. I'm drawing these sound waves crooked just so you can see them. They'd really be right on top of each other along this line. But that takes another amount of time, so it keeps doing this, and it knows that you'll have points right here. Difference between interfaces right here, an interface between 2 different tissues. And you can get an image of this whole cross-section if you just have a transducer that sends out pulses along this whole face of the transducer. You can image this whole region. So you can start imaging all these points. You can figure out what is inside of here, what's the shape of it, what are any particular lesions or lumps going on inside of here. So that's ultrasound. That's one way it's useful. It actually uses ultrasound frequencies. You might wonder why. Why would we have to use ultrasound? Well, I mean, one reason why is if you took this transducer and you were using audible frequencies, you take this noisy thing, you hold it up to a patient, that patient's going to be like, you sure that's okay to hold up to me, doc? So that might be upsetting. But another more practical reason for using ultrasound is high frequencies, and that is to say low wavelengths. And these two are the same because remember, speed of a wave is wavelength times frequency. So if the frequency is high, the wavelength is low. Because the speed's not determined by either of those, the speed is determined by the medium itself. It turns out for high frequency, low wavelength, you get less diffraction. And diffraction is an enemy of making clear pictures because what diffraction is this is a spreading out of waves. So if I had my wave coming in here, wave coming in, and there was some sort of barrier, and let's say this barrier is right here and it's got a small hole in it, waves spread out. But if it's a high frequency wave, it won't spread out much. It's going to enter through this hole and it'll spread out a little bit. It's going to get a little bit wider. But if it were a low frequency, maybe audible region, high wavelength, the spreading would be bigger And this would be a problem because if it spreads out, think about it. If this wave was coming in here, and this wave was coming in here, and then it curves around corners. So another thing diffraction does is it causes waves to curve around corners. The spreading happens. Now you've got all this bending of sound waves reflecting off of things, confusing the transducer. You get a blurry image. That's why we want to use high frequencies. There's less diffraction. You get a clearer image. So this is one application of ultrasound for medical imaging.